So today's lecture is about perfect graphs. Perfect graphs were born from deliberations about what can cause the chromatic number of a graph to be large. So as you know, there can be local reasons and global reasons, where global reasons is pretty much the same as what doctors mean when they say something is psychosomatic. That means they don't know the reason. So a chromatic number, the chromatic number of a graph can be large even though nobody knows why. In particular, there is no local reason, such as a complete subgraph, for example, which is more than enough justification for the chromatic number to be large, if that is large. And perfect graphs were born of this quest to understand, if not the global reasons for large chromatic number, then perhaps learn something from assuming that there is a local reason. So perfect graphs are one way of defining a class of graphs where the reason for large chromatic number always consists of the presence of a complete subgraph. So we could tentatively define this class by requiring that for all its elements G, the chromatic number must be no bigger than the clique number. The clique number is the largest size of a complete subgraph. So omega of G, which we usually abbreviate just as omega when there's a graph G that we're talking about, that's called the clique number of the graph G. Now, there are conflicting notions of clique. Most people in graph theory use clique as a synonym for complete subgraph. Some authors write clique for a maximal complete subgraph, one that cannot be extended to a larger complete subgraph. I don't use it at all in the book and always speak of complete subgraphs, but today I might speak of cliques, and when I do, I just mean any complete subgraph. And an analog of that, or precisely the clique number of the complement, G bar, is the independence number of G. And that's the largest size of a set of independent vertices. Right, so the clique number of the edge complement of G. That's the independence number alpha. And we'll likewise often write just alpha for alpha of G when G is a particular graph we're studying. Right, now, tentatively I said we could define a class by just asking that its elements should have a chromatic number no bigger than the clique number. It can't be smaller. But that would be rather a boring class of graphs. We couldn't say much about the structure of its elements, because after all, you could take one of those mysterious graphs that have large chromatic number and large girth, in particular no big cliques, and then say its chromatic number is 105, and then you could put next to it a clique of order 105, and suddenly that graph, that union of these two graphs, will be in your class. And so, since that is so, there wouldn't be much hope in working out the structure of graphs in that class. And for that reason, the class is artificially closed under taking induced subgraphs. So a graph is called perfect if it and all its induced subgraphs have a chromatic number no bigger than their clique number. So why are we closing under induced subgraphs and not under any subgraphs? Well, if we did, there wouldn't be many graphs left. For example, complete graphs would not be perfect, because obviously they contain these mysterious graphs as subgraphs. So that wouldn't be an interesting class either. So this is the notion of perfection. Think of it as all subgraphs, all induced subgraphs, can be colored with their clique number many colors. Right? Okay. There is more to perfect graphs than meets the eye when you see the definition. There is some duality about them in a sense that maybe isn't quite understood. Many people understand a lot more about it than I do. There are connections to optimization, also to duality in optimization. Latte Lovers has written a lot about this many, many years ago already. And you can read, if you're interested in optimization, about this aspect that comes from perfect graphs in his works. So perfect graphs are more important than one might think just from the definition and from this motivation via the chromatic number mystery. And they have been studied extensively, particularly in the last 20 years, and I'll get to that in a moment. Examples, bipartite graphs are perfect, chordal graphs are perfect. You know what chordal graphs are? Sometimes called triangulated graphs. So chordal graphs are graphs that don't have induced cycles other than triangles. So whenever you have a cycle, you find a chord, unless you're in a triangle already. Right? Those graphs are chordal graphs. And you can build all chordal graphs by sticking together complete graphs in a tree-like way. Using that building mechanism for induction, one can show that these are perfect, because complete graphs, their building blocks are perfect. And then when you stick two graphs together in a complete subgraph, then if they were both perfect, they'll remain perfect, and so on. So these are examples. None of these examples are part of this course, but I think I'll just skip that here to get to the interesting bit. The really interesting bit is what I cannot cover, and that's called the perfect graph theorem, or the strong perfect graph theorem. There's also a weak one, which I will cover and prove to you. And that characterizes the perfect graphs by forbidden induced subgraphs. Now, what does that mean? It means that it identifies some particular imperfect graphs, and then the theorem says that a graph is perfect if and only if it contains none of those as an induced subgraph. And the ones in that list are the odd cycles and their complements. We'll get to that in a moment. So why is it possible in general, if you have a class of graphs that's closed under some relation, such as induced subgraph, but it could be anything. It could be topological minor or minor or subgraph. So if you have a class of graphs closed under a transitive relation, then it can be characterized as the class of graphs that don't contain blah. And what can you take for blah? Well, you could take the complement. You could take all the graphs that are not in it, right? These graphs can't contain those because this class is closed, so anything it contains is in that class. And if something is not in that class, well, it must contain one of those because it is one of those, right? And you can get away with just the minimal elements under this relation of the complement and forbid just those, because if a graph isn't in that class, well, it's somewhere in here, and it take a minimal thing below it that still isn't in the class, that'll be in that set. So your graph that isn't in the class will contain a minimal such thing. That's because all the graphs are finite, and taking smaller ones will leave you with a minimal element. Right? When the graphs are infinite, you can go down forever, perhaps. You get different classes all the way, infinitely often. Infinite graphs are much nicer than finite graphs, but that's a secret. Okay, so any class of graphs that's closed under some transitive relation can be characterized by the minimal elements not in it, which are often denoted by something like forb for forbidden graphs for G with respect to this particular relation. So Kuratowski's theorem is your standard example. Planar graphs closed under taking minors are those that don't contain one of two non-planar graphs as a minor. Okay, so how about the perfect graphs? Well, as I said, the theorem is that they're characterized by the odd cycles of length at least 5. I think I forgot to say that earlier. The odd cycles of length at least 5 and the complements of those things. Right? A graph is perfect if and only if it contains no odd cycle of length at least 5, and no complement of a cycle, an odd cycle of length at least 5, where complement is the edge complement. Right? So that's the perfect graph theorem, or the strong perfect graph theorem. It has a long history. It was open for many, many years, conjectured by Berge, and proved not so long ago by Chudnovsky, Robertson, Seymour, and Thomas. Okay, it implies what used to be called the weak perfect graph conjecture. Lovers proved that in 1972, when your grandparents were in the sandpit or something. That says that a graph is perfect if and only if its complement is perfect. So, of course, if and only if. So, if a graph is perfect, then its complement is also perfect. That follows from excluding these particular graphs, which are commonly, popularly known as odd holes and odd anti-holes, these cycles of length at least 5, odd cycles of length at least 5. Since that condition of not containing one of those is closed under taking complements, because the complements of these forbidden things are also forbidden, the class they characterize by forbidding them is also going to be closed under complements, and that's the weak perfect graph theorem. To prove the perfect graph theorem, we need a famous lemma, the replication lemma. I'll tell you what it means first, then I'll say a couple of words about it, and then we'll prove it. It's not going to be hard. So what does replication mean? You have a graph and a vertex x, and x has some neighbors. Then replicating x means adding a clone of x to this graph call that little x prime, and we make little x prime adjacent to precisely the neighbors of x and to x itself, right? And then sometimes if this original graph was called G, we might call this G prime, but G prime will have other uses later as well. Okay, so and the replication lemma says that if G is perfect, then G prime is perfect as well. When we look at the proof of this lemma, it'll all be very simple and easy and sort of like the result of playing around a little bit and noticing that the various bits of information one has gathered neatly click into place to give this statement. What seems much harder to me is to come up with this statement. And indeed, as we use it later in the proof of the perfect graph theorem, I think the idea that leads to the formulation of this lemma is a very clever idea. And so coming up with it, I thought was a big thing. But historically, it's not like that. Historically, everything else was there before. And then it was known that all one needed to prove, or all it boiled down to, was this lemma, and indeed that the assertion of the perfect graph theorem that a graph is perfect if and only if its complement is perfect is equivalent to the assertion of this lemma. And this lemma seemed so unlikely to the person who was mostly thinking about it at the time, who was an optimizer, Fulkerson, that he gave up at that point and thought, oh no, if this statement, the perfect graph theorem, is equivalent to that, that can't possibly be true. So he didn't think further about it, or so the story goes, until Lovász actually did prove it. And then there's this little anecdote, how does it go, that Burge, who invented perfect graphs and both perfect graph conjectures, the weak and the strong, where the weak has turned into this theorem, wrote to Fulkerson that apparently this young Hungarian by the name of Lovász had audaciously dared to prove this lemma that couldn't possibly be true, and therefore had proved the perfect graph theorem now. And so the anecdote goes on to say that Fulkerson said, oh, well, okay, in that case I can do it too, and he went home and he did it, and so that's the anecdote. Anyway, why did Fulkerson apparently think that this couldn't be true? As far as the experts tell me, the reason lies in the fact that the mere assertion that chi is at most omega, that you can color a graph with at most its clique number colors, is not preserved under replication. So if we just take if we replace perfection with the property that chi is at most omega, then that is not preserved under this operation. And it's an exercise to come up with an example where this does indeed fail. So what's the difference? The difference is that here, with perfection, we're assuming this property that chi is at most omega, not just for G, but for all the induced subgraphs of G as well. And one needs that, because without this assumption, the replication does not preserve the property. It's an easy exercise to, once you sort of think about it, to come up with a counterexample. So I won't give you that counterexample, but just prove the replication lemma now. The assertion is clear, is it? Yeah. Okay, so proof of the replication lemma. So we have to show that for every induced subgraph, H, we can color that subgraph with its clique number of colors. So so let's look at such a subgraph of G prime. Okay. Every induced subgraph of G prime. We're assuming the same for G, and we want to prove it for G prime. Right? Right, so where could this subgraph lie in G prime? Let's look at a few cases. If X prime is not in it, if the subgraph doesn't use the new vertex, well, then it's a subgraph of G. And subgraphs of G have this property because G is perfect. So that's easy. And similarly, if little x is not in our subgraph, then we can replace x with x prime and for the same reason find that H can be colored with omega of H colors, right? So if X is not in it, then X prime then H is some subgraph of G prime that may or may not contain this vertex X prime. If it doesn't contain it, it's again a subgraph of G itself, and therefore the assertion holds by the perfection of G. But if it does contain X prime, since it doesn't contain X, we can find an isomorphic subgraph of G, namely just by replacing X prime with little x. And that isomorphic subgraph can be colored with its clique number of colors because G is perfect, and so we're done again. And if neither of them, no, sorry, if both of them are in H, but H is a proper subgraph of G prime, then we're also done. Why? Well, if H is genuinely smaller than G prime, and both X and X prime are in it, then no matter what else H contains in here, since it's induced in G prime, it will have arisen from some proper subgraph of G by replicating X. Right? If X and X prime are both in it, then not all of this can be in it because H is smaller than G prime, but those two vertices are in it. Then this smaller subgraph was obtained by a genuine, by a proper subgraph of G by replicating X. So that's also easy. So, what about G prime itself? Now, there's an easy case in that too, and that is if the clique number has gone up. So if G prime has bigger cliques than G, so if omega of G prime is bigger than omega of G, which we'll call omega from now on, They were also done because we can color G itself by omega colors by assumption, and now if we're allowed one more color, we can just use that for X prime. So what remains to be considered now is that H is the entire G prime, and omega of G prime is no bigger than omega of G, but is omega itself. Okay, and what we want now under this assumption is a coloring of G prime with only omega colors, with this many colors. Now we do have a coloring of G with omega colors because G is perfect, so let's consider that. Consider any omega coloring of G. And then in that, consider the color class that contains this little vertex X. It's some color class, give it a name, big X say, and then we'll give a name also to big X minus little x. And call that X prime. Right. Now, every omega clique has to meet every color class because we only have omega color classes. Right? So every k omega in G meets every color class, in particular X. Right? But not in X, little x. Why not in little x? Well, if it did, if we had a k omega that included little x, then in G prime, we would have a k omega plus 1. But we don't, by assumption, here by this assumption. So every k omega meets every color class, in particular the color class X of this particular omega coloring that we have, but it doesn't meet it in X. So, I don't know, here's one k omega, there's another, and so on. They might intersect wildly elsewhere, but each of them has to meet X. But now, what's the clique number of G minus X prime? If we just delete this portion here, if we delete that from G, well, this X prime meets every k omega. So if we delete it, then the clique number goes down. So omega of this has gone down, is less than our omega of G. But that is the same as the chromatic number of G minus X prime. By the perfection of G. And now comes the trick, or the idea that I think is very pretty. This is the same as the chromatic number of G prime minus X, because the graphs are isomorphic, right? So G minus X prime is isomorphic to G prime minus X. G minus X x prime, we just delete this. If in G prime, we delete this and little x, we get exactly the same thing, because in G, the little x prime is not there, but in G prime it is there. You see that? Okay, so that's good news. The chromatic number of G prime minus x, the whole x, including little x, is less than omega. Right, so we can color the entire set X in G prime with right, the one that is not used in this coloring now of G prime. Okay, questions? No. Pretty easy. Yeah. Okay, I'll whiteboard and then we'll prove the perfect graph theorem. So the perfect graph theorem says once more that if G is perfect, then the complement of G is perfect, right? And so proof. We have to show for every induced, let me call it H bar straight away, induced subgraph of G bar that the chromatic number of H bar is at most its clique number. That we can color it with its clique number many colors. So that's what we have to show. Right, so let's just write down in words what this means. What does this mean? It means that we can cover the vertices of H bar, can cover the vertices of H bar by omega of H bar many independent sets, right? That's just writing out what this means. Now let's rephrase that in terms of H. So we can cover the vertices of H, which are the same as the vertices of H bar, by alpha of H many cliques. And as I said earlier, when I say clique, I just mean complete subgraph now. Okay. That is easy. By induction on the number of vertices in H, if in every induced subgraph of G, there exists a clique that meets every independent set of this size, every largest independent set. Okay, I've written that out for you, so let me reveal it. Okay. If it's true, so if star, I claim that proving this is easy by induction if star holds. And why is that? Why does that make the proof easy? Well, consider the subgraph H, and then some independent set of largest size. Out of H. Right. If we can find a clique that meets every such largest independent set, in particular it will meet this one here, so that's our first clique, K1, and then it has to meet that. Okay, then we delete it. Then we get an induced subgraph of this H. Let's call it H again. And again, if star holds, then we can find another clique that meets every largest independent set. And notice that what remains up here is still a largest independent set, right? Because our earlier clique met every one of them. So each of them got reduced, so there are no independent sets of this size left after we deleted our first clique, because they all got hit. So what remains here is still a largest independent set. We can find another clique that meets every largest independent set, in particular this one, undeleted. And so we carry on, if star holds, until we've eaten up all the vertices of our sample independent set of largest size. And what we have found is precisely what it says here. We found a covering of the vertices of H by this many cliques. And that's what we needed, right? So that's what we want. Is that okay? So if it is okay, then all I'll do now is prove star. Star. Assuming that G is perfect. Right? Here's what seems like a completely irrelevant remark. So irrelevant observation. This is easy if all the sets in curly A are disjoint. All sets in curly A are disjoint. Right? All these largest independent sets. Why is that? Why does that make it easy? Well, then what does H look like? There are all these independent sets of largest size, alpha of H large, and there are curly A many of these sets, all of them. if they're all disjoint, then the chromatic number of H cannot be smaller than the number of colors we used here. And that is for the following reason. These may or may not cover the entire vertex set of H, doesn't matter. My claim is that with fewer colors, we cannot even color these vertices. In particular, then the chromatic number of H, if H is indeed larger than what we've covered, cannot be smaller. So with fewer colors, why can't we even cover these sets here? Well, because if we use fewer colors than we have used here, then we have classes here, then one of these, because these classes are disjoint, one of these would have to be bigger, right? If we use fewer of them, then one of them has to be bigger. But we can't have one that is bigger because they're all of maximum size, right? So this portion of H that we have covered by these largest independent sets, if they're all disjoint, cannot be colored with fewer colors. So, by assumption that G is perfect, omega of H is no smaller than the chromatic number of H. And then now, just take any maximum clique, clique of maximum size in H, and then it hits every element of curly A, every largest independent set, and that's exactly what star requires. Right, we can find a clique that meets every independent set of size alpha. Okay, so it's easy if all the largest independent vertex sets happen to be disjoint. Why did I call it an irrelevant observation? Well, because, of course, they're never all disjoint. It's a completely artificial example. But now comes the crucial idea, and that is if not, make them disjoint. Okay, so let me tell you what I mean by that. So we define a new graph H prime on the union, the disjoint union of A. Now, if A is not disjoint, then I can't write the disjoint union, so I give it a new name, A prime, and A prime is just a set of clones. So it's a set of A primes such that A is an A. So once more, what is curly A prime? We have our curly A, it has certain sets in it. And we take each one of these sets once, and take it as vertices for H prime. And then we take the next set in there that might intersect the first of the sets we picked in G, but never mind. We take a clone of the second one, call that second set prime, and place it next to the first set disjointly. Right? So we're just taking copies of the sets in curly A, one copy of each one of them, and we write them all next to each other disjointly. So that's going to be the vertex set. And the edges of H prime are the following. For every vertex V of H, we have the set which I want to call UV, and that's the set of all, and we make that complete. So once more, example, in H, we have, say, some sets in curly A. One is here, maybe it has these three vertices. Then there's another, it has these three vertices, and then there's yet another. There's these three vertices, so let's call these A1, A2, A3. And then in A prime, we make them all disjoint. So A1 prime is here, A1 prime, A2 prime is next to it, and A3 prime is next to that. And now this little v here, this was in all of the A's, so it's in every copy. And I call this U little v. Right, and that little u, for example, is in two copies, A2 and A3. So that is u little u. And then there are some other vertices in the AI prime as well. Right, is the definition clear? And in this new graph H prime on the disjoint union of the sets in A prime, we turn these sets that all come from the same vertex of G into complete subgraphs. And join U to UV completely whenever UV was an edge of H. Right? So if there was an edge in H here, then we'd draw in all the vertices in the u little u to all the vertices in the u little v like this, and these had been made complete before as well. So. Okay. Now, some observations about this. And the first one is that the independence number of H prime is no bigger than that of H, and no smaller. So why is that? The copies of the sets A and curly A, these copies here are still independent sets. Right? We never added an edge inside one copy, only between different copies. So these are still independent sets, so the independence number of this is at least the independence number, but we can't have any bigger independent sets in H prime. Because take any independent set in H prime, well, it hits every UV in at most one vertex because they're complete. If you take a vertex in one UV and take another vertex in some UU, if they were adjacent in H prime, how can vertices from different UVs be adjacent? Well, only if their indices are adjacent in H. Right? So we can't have any bigger independent sets. Okay, let's keep that in mind. And now, well, and also notice that H prime arises from H by replicating. And this is where the idea of replication comes from. Well, once you've seen that this proof works, this is how the idea, where it comes from. But can you see the fact that H prime arises from H by replicating vertices? Namely, every little v gets replicated order of uv often. Right? And they all, replicating vertices makes them all adjacent. So from every little v, we get a clique on this set of vertices. And the point is we needn't know how big these sets are, or where they lie, or anything at all. So they form cliques, and since replicated vertices inherit the neighbors from the vertices that they replicate, also edges that were present in H generate edges between the corresponding sets U, and UV. So yes, H prime arises from H by replication, so H prime is perfect. Okay, and now we can do exactly what we did here. So now we observe that because the elements of curly A prime are all disjoint, right, like here, the chromatic number of H prime cannot be smaller than the cardinality of H curly A prime. So the chromatic number of H prime cannot be smaller than the cardinality of H prime, which of course is the same as the cardinality of A, sorry, not H, A, curly A, right? And since H prime is perfect, this is no bigger than the clique number of H prime. So, there's a K prime, a clique K prime and H prime, namely any clique that realizes this clique number, which, being a clique, cannot hit any set in curly A prime more than once, but it has as many elements as curly A prime has elements. So it must meet every element of curly A prime. and now we're nearly home, as you probably suspect. These cliques, what do they look like? Such a clique meets some UVs. It's easy to see that if it's a maximal clique, which of course it must be here, but never mind, then it contains every UV that it meets, but we don't need that. So it meets some UVs, and then whenever it meets two of them, the corresponding indices form an edge in H, and that's what we need. So there's a clique K in H. That means every set in curly A. Right, and how do you define this K? Well, as I said a moment ago, so that is just a set of V such that K prime meets and therefore contains UV. Right, and those are clearly complete in H by this. And it meets every set in curly A because the big K prime meets every set in the clones. So they're just the copies. And that's it. Right, because that's exactly what assertion star says, that H contains a clique that meets every A in curly A, every set in curly A. And that's the end of the proof of the perfect graph theorem. So it's all really quite easy once you know how to do it. And what I find fascinating is how to come up with this totally crazy project of making these sets disjoint, having observed that it would be so nice if they were. Right, so we just create another graph, and then we know for that graph we can prove it if indeed that graph is perfect. And all that remains to show is that this blown up graph is indeed perfect if the original graph was perfect. And that's the assertion of the replication lemma. And so it seems natural to arrive at the replication lemma and then sit down and prove it, unless you know too much about optimization and so on, in which case you don't believe in it and stop there. So this is not to say that Lovis didn't know a lot about optimization too. He certainly does now. But anyway, that's the end of the proof. Any questions?